Okay, so this is now the continuation of our discussion in power plant engineering, the performance of diesel engine. So this is maybe the last part of the presentation. This is part number 5. Okay, so let us now continue. So by this time we are now going to tackle engine efficiency. Okay, so wherein this engine efficiency is divided also into several parts or 4 parts. So one is the indicated engine efficiency. The next is brake engine efficiency. The other is the combined engine efficiency, and the last is the plant engine efficiency. Okay, so basically, the engine efficiency is defined in terms of the thermal efficiency and the theoretical thermal efficiency of the ideal cycle multiplied by 100%, or NE is equals to the brake thermal E over the theoretical thermal efficiency ET. Okay? So where the brake thermal in our previous discussion, it is defined as the power divided by the energy chargeable, or simply 3,600 multiplied by the power divided by the mass flow rate of the fuel multiplied by its heating value. Or simply, the theoretical cycle or the theoretical efficiency is defined as 1 minus 1 over Rk raised to K minus 1 multiplied by the factor Rc raised to K minus 1 all over K Rc minus 1, where Rk, of course, is the compression ratio and Rc is the cut-off ratio of the engine. Okay, so let us now proceed to indicated engine efficiency. So where this NEI is equal now to indicated thermal efficiency divided by the theoretical thermal efficiency. So by this time, the denominator now here is constant. Okay? So, knowing that the indicated thermal efficiency is equals to 3,600 multiplied by IP over MF multiplied by HB. And the equation now is EI over ET. Okay? So, next is the brake engine efficiency. So, the derivation of the formula here are the same in all types of engine efficiency. Okay? So, for brake engine, our numerator here is, of course, the brake thermal efficiency, and the numerator is, or denominator rather, is the theoretical thermal efficiency. Okay? So, next is combined engine efficiency. So, NEC equals to combined thermal over the theoretical thermal efficiency. Okay? And the last one is plant engine efficiency. So, NEP equals to EP, or the plant thermal over the theoretical thermal efficiency. Okay? So the heat balance now of the diesel engine. So the heat, of course, is divided into several parts of the engine. Okay. The first is the useful output, or this is the brake power. So basically, the assumption for the brake output is 34%. So this is just an assumption. Okay? The cooling loss, that is almost 30% of the energy chargeable to the engine. The exhaust loss is almost 26%, radiation, friction, and other unaccounted losses, equivalent to 10%. So, totally, so this is 100% equal to energy chargeable of the engine equal to mass of fuel multiplied by the heating value of the fuel. So, if we now calculate the useful work, so that is mass of fuel time HB multiplied by the percentage of the brake output or the brake power. Okay? So, if the mass of fuel and heating value are known. Okay? So, for cooling loss, that is mass of fuel times heating value multiplied by 30%. Or that is also equal to the mass of cooling water, or circulating the engine, multiplied by specific heat of water, multiplied by the change in temperature of the jacket water. Jacket meaning the leaving temperature minus the temperature of water entering the engine. Okay. So, for exhaust loss, of course, this is the heat carried by the exhaust. So, that is mass of fuel times heating value multiplied by the percentage, which is 26%. And for radiation and other unaccounted losses, friction, that is equivalent to 10% also of the energy chargeable to the engine. Okay? So, let us now consider an example. So, in order for the formulas above or in the previous discussion be applied. Okay, so let us now take this example. A single cylinder, single acting 305 mm, 460 mm 4-stroke cycle diesel engine was tested for an hour and the following data were obtained. Okay. So, mass of fuel, 7.5 kilogram. Take note, the time of the test is 1 hour. Okay? So, the total revolution is equals to 12,120. The jacket water is 600 kilogram. Rise of temperature of jacket water is 28 degrees. The length of the card, so length of indicator card, 7 centimeter. The scale of indicator card is 80 megapascal per meter. The torque due to brake load is 120 kilogram meter. Heating value of fuel is 44,200 kilojoules per kilogram. So, fine. Okay? So, indicated power, brake power, and mechanical efficiency. Next is indicated specific fuel consumption or indicated fuel rate. Okay? So, other term for this is indicated fuel economy. Okay? So, they are all the same. Okay? Other is brake specific fuel consumption or brake fuel rate or brake fuel economy. The other is the percentage of total heat supplied converted into brake power, and then the percentage of total heat absorbed by the water jacket, and then the percentage of heat loss by friction, exhaust gases, radiation, etc. Okay? So, let us now make a breakdown of the given. Okay? So, C, or the number of cylinders 1. N is 12,000, 1,220 revolution per minute. Okay? So, that is equivalent to 202 revolution per minute rather. So, this is revolution per hour. Diameter is 305. Length of stroke is 460 mm. Mass of water is 680 kg per hour. Torque is 120 kg meter, and so on and so forth. Okay? So let us now proceed to the solution. So getting now the indicated power. So from the definition of PMI, okay? So PMI is equals to getting the indicated mean effective pressure. So that is equivalent to substituting values equivalent to 628.5 kilopascal or 0.6285 megapascal. And then solving for the indicated power, substituting values from the original equation. So indicated power equals to PMI multiplied by the piston displacement. So substituting values, converting units of millimeter to meter, and then seconds to minute or minute to seconds rather. The indicated power now is 35.6 kilowatts. So solving for the brake power. So since the torque are already known or is already known, and of course the speed of the engine, brake power now equals 24.9 kilowatts. Okay, so getting now the mechanical efficiency. So from the definition, mechanical efficiency is equals to brake power over indicated power. So therefore, the mechanical efficiency now is 70%. So this is quite low. Okay? So let us proceed to the indicated fuel rate. So IFR. So that is equivalent to mass of fuel divided by the indicated power. So knowing the mass of fuel, which is 7.5 kilogram per hour divided by 35.6, the value now of the indicated fuel rate is 0.21 kilogram per kilowatt hour. And then getting the brake fuel rate, substituting values, where the brake power is 24.9, the value now is 0.3 kilogram per kilowatt hour. Okay? So, another. So, for the brake thermal efficiency formula, that is AB, also 3,600 multiplied by the brake power over energy chargeable. Okay, so getting now the brake thermal efficiency, substituting values, the value now of the brake thermal is 27%. Okay, so for the heat absorbed by the jacket water, so that is QJ multiplied by the mass of water, CP water, and the delta T of water. So getting now, or substituting values, the value is 22.16 kilowatts. Okay, so let us now get the percentage absorbed by the jacket water. Okay, so that is QG over energy chargeable. So 22.16 multiplied by 3,600. So this is not 36,000. This is just 3,600 divided by 7.5 multiplied by 44,200 multiplied by 100%. Therefore, the heat absorbed by the jacket water is equivalent to 24% of the energy chargeable to the engine. Okay? So, another is the percentage of exhaust friction and radiation. So, knowing that the energy chargeable equals to brake power equal to the Q exhaust equal to plus Q jacket plus Q friction radiation. Okay? So, combining now the heat carried by the exhaust plus the heat by radiation and other unaccounted losses, QEFR now, Q exhaust, friction and radiation equals to 7.5, the mass of fuel entering the engine multiplied by the heating value of the fuel minus the percentage of Q absorbed or the heat carried by the jacket water. That is now equivalent to 24.9 minus 22 0.16. Okay, so is now equivalent to 45 kilowatts. Okay, so that is now the heat carried by the exhaust, friction, and radiation. So 45 kilowatt divided by the energy chargeable, that is equivalent to 48.98%. Okay? So thank you very much. So that ends my presentation.